very much. Okay, so today I'm going to talk about an onshore formulation of chiral perturbation theory. And the subtitle is really the fall and rise of S-matrix theory. And before I start, I want to give the credit to my collaborators on this subject. They are Lin Dai, who is a postdoc at Israel, Daleo, a postdoc at UC Davis, Tom Ian, faculty at Duke, Abhishek Malhotra, a postdoc at Munich, and Zewei Yin, who just graduated last year from Northwestern and is now postdoc at Uppsala. Okay. All right. So let's see if I can flip my page. Okay, good. So chiral perturbation, I think it's fair to say that chiral perturbation theory is the mother of modern EFTs. Okay. It's a low energy effective theory of QCD and an integral component of our understanding of many nuclear processes. And it describes interactions of mesons and baryons at an energy scale of 1 GeV or below. And in my view, really is the most elegant example employing modern techniques of effective field theories. And so let me clarify a little bit what I mean by modern techniques. What I mean is that the philosophy of modern EFT is that in most cases, symmetry consideration alone is sufficient to capture the long wavelength dynamics of a physical system. So for chiral perturbation theory, the symmetry is SUN left times SUN right chiral symmetry. Okay, and the short wavelength fluctuations are encoded in uncalculable Wilson coefficient. And in addition, a power counting scheme must be supplied to organize the relative importance of different effective operators. And in chiral perturbation theory, the power counting is the derivative expansion as is well known. Okay. And so the history of chiral perturbation theory is described in the inaugural lecture of this very nice seminar series by Professor Weinberg. And he even wrote it up and put it out on the archive. And it's really fascinating to read through these historic anecdotes and historic accounts on the birth of chiral perturbation theory. So I want to share a few interesting bits and pieces with those who were not at the lecture. So for example, Weinberg mentioned that the phenomenological Lagrangians were developed as merely labor-saving devices, guaranteed to give the same results as current algebras, okay? And he also said that no one took these theories seriously as true quantum field theories at the time. This is back in the late 1960s. And the soft pion theorems have been successful not only in agreeing with experiments, but also in killing off a competitor of quantum field theory known as S-matrix theory. Therefore, it's really fair to say that the birth of chiral perturbation theory contributed to the downfall of S-matrix theory. Okay. And while I emphasize that this is the modern EFT, but what I mean by modern here really refers to things that were first developed more than half a century ago. For example, the paper by Weinberg on nonlinear realization of chiral symmetry was dated in 1968. Okay, and chiral perturbation is an EFT about Nambu-Goldstone bosons, which has an even longer history, dated back to 1960s by Nambu and Goldstone. And the textbook example of Nambu-Goldstone boson starts with the following Mexican hat potential, that we start with a complex field phi with a Mexican hat potential, okay? And the ground state of the potential, there is at the bottom of the circle here, and there is an infinite number of ground state labeled by the polar angle alpha, okay, on the XY plane, okay? And once an alpha is chosen, the rotational invariance of the potential is hidden or is quote unquote broken spontaneously, okay? And to see the Nambu-Goldstone boson explicitly, what we do is we go to the polar coordinate, we write the complex field in terms of a radial mode and an angular mode, okay? And in this parametrization, the ground state is that the radial mode has a vacuum expectation value of V, whereas the angular mode has a vacuum expectation value parameterized by the angle alpha. That is, we picked one particular ground state along the circle at the bottom here, okay? And this is something that we're familiar now, that the next thing we do, we expand with respect to the ground state, we shift the rho to rho plus the VAV, and pi goes to pi plus the VAV. Then under rotation by theta angle of the ground state, okay, then the ground state in pi gets shifted from alpha to alpha plus theta if we rotate the ground state by angle theta. And as you can see, because we shifted the pi field from pi to pi plus the ground state of pi, so this rotation by theta angle is actually equivalent to shifting the pi mode by the constant theta. That is, a rotation from one ground state to another ground state is really equivalent to shifting the pi mode by pi goes to pi plus theta. Then the rotational symmetry really implies the dynamics of the system must be independent of this constant shift, okay? And so now this is known as the shift symmetry in the Nambu-Goldstone bosons. And you can see obviously that the shift symmetry forbids a mass term in the pi mode. Therefore, in fact, it forbids any potential on the pi mode, and therefore the Nambu-Goldstone boson is massless due to the shift symmetry. Okay, and so we could generalize to more complicated cases. Okay, for example, we can consider n real scalar. Okay, phi going to phi 1 through phi n, and again we can write down a similar Mexican high potential. Okay, like this. And then the ground state of the phi field, we can pick a particular ground state at the bottom of the infinite number of ground state. And in this case, the residual broken symmetry is OM minus 1, whereas the broken symmetry or the total symmetry of the system is really ON group. So the symmetry is broken from ON to OM minus 1 spontaneously, okay? And the Nambu-Goldstone mode can be parameterized in many different ways. One way is to parameterize it in terms of the sigma field and the pi 1 through pi n minus 1. And sigma field is related to pi mode as square root of 1 minus pi squared. And in this case, from the kinetic term of the phi field, we can derive the kinetic term for the pi field, okay? And the important observation here is that interactions of Nambu-Goldstone boson in general are horribly nonlinear, as you can see from this equation here. And moreover, the Nambu-Goldstone modes are always derivatively decoupled. We hear people say this all the time. Nambu-Goldstone bosons are derivatively decoupled, and you can view this as a consequence again of the shift symmetry, because if it has to be shift symmetry symmetric, it has to be derivatively coupled. Okay. So that's sort of so far. This is a usual story, textbook story that I think everybody knows, and I'm sort of repeating here just first to bring everybody to the same page. Second, I want to contrast, make a contrast with the on-shell approach that I would be talking about later today. Okay. And more generally, okay, there is a well-defined procedure to write down Nambu-Goldstone effective actions for arbitrary symmetry breaking pattern due to Coleman, Callan, Weston, Zumino, done back in 1969. Okay, And the procedure dictated by CCWZ is that we pick a non-linearly realized group G and a subgroup of H of G that is linearly realized. And the jargon here is that the linearly realized group is the unbroken group, and the non-linearly realized group G is the broken group. Okay, and then we pick the generator that sits in the broken direction and write it as in the exponential parameterization together with the pion field. And in this notation, the pions are really coordinates on the cosine manifold G mod H. This again, this is all contained in the CCWZ paper. And then the action of the pion, okay, under a group element G is such that G acting on C can be decomposed into the C prime times an element that is in the unbroken group. And the C prime is the pi prime that is transformed under the action of G. And there is a special case when we pick G to be also in the broken direction, parameterized with some constant epsilon A, then it's easy to see that to the first order in epsilon, the pi prime equals pi plus epsilon. And this is the shift symmetry that we've been talking about. Except that in the more general case, you know, there are many more terms that could come after the shift symmetry that are rarely discussed. And this is because in CCWZ, we never have to worry about these dot terms, okay? And the reason we don't have to worry about them is because CCWZ looked for objects that had simple transformation properties under the action of G, okay? Because the pion itself has very, very complicated and nonlinear transformation laws under the action of G. So that's not something we want to deal with. Instead, we want to deal with something that has simple transformation properties under the action of G. And these are contained in the so-called Cartan-Moyer-1 form, okay? You look at the C dagger d mu C. This is an object that sits in the Lie algebra of the full group G, and you can decompose it into the broken direction X and the unbroken direction T, okay? And the object in the broken direction is called the Goldstone covariant derivative because it has a simple transformation law under the action of G, which is just U d mu U inverse. Whereas the object in front of the unbroken generators are called the associated gauge field because it has a similar transformation law to the gauge field under the action of G. Okay, and once we have these two objects, d mu and e mu, we know how they transform under the action of G. That means we know how to build the complete effective Lagrangian, apart from the topological terms that I would talk about later. For example, at the leading order, the lowest, the two derivative term in the effective Lagrangian is given by a trace of d mu d mu. Okay. So the reason I want to sort of go through this CCWZ procedure is to highlight the fact that in CCWZ, you can see that the interaction of Nambu-Goldstone boson depends both on the full symmetry group G, because you have to know both X and T. You have to know both the broken generator and unbroken generator. So you have to know the full symmetry group G in the UV, and as well as you have to decide what's broken, what's unbroken. Therefore, you have to know what's the unbroken symmetry group H in the infrared. Okay, this is, again, if you have ever played with CCWZ, you know that you always have to know what G and H are before you set out to construct the effective Lagrangian. So just to show you some very concrete example that I would come back to visit later, that I'm showing you, okay, two different G's and H, okay, and both of which contain a complex Nambu-Goldstone field that is charged under a U1 subgroup of H, okay. The first example, I would take the G mod H to be SU2, mod U1. So the unbroken group is just H itself. And the Goldstone mode is a complex field, and this is what the effective action of the Goldstone field that you would get from cranking the machinery of CCWZ. And I want to compare these to also a complex field, okay, in a different coset such as SU5 mod SO5, okay. And I also, in this coset, there is in fact, there are many complex Goldstone field in this coset, but I want to compare one, pick one, and then look at the effective action of that complex Goldstone. And if you, again, you can just do this, and I'm going to show you the results. So this is the effective action of a complex Nambu-Goldstone field in the SU5 mod SO5 coset. So if you look at these two effective actions, you see that there's some similarities, but there are also a lot of places that are very different. And this is sort of meshes well with the expectation from the CTWZ that the Nambu-Goldstone effective actions depends on both the G and H, because here we pick different G and different H, so the effective action look different. Okay, so let me just recap very quickly the quote-unquote conventional wisdom from the last half a century, because pretty much everything I talked about so far we knew from half a century ago. So the spontaneous symmetry breaking occurs when the ground state is not invariant under the full symmetry of the system, and the Nambu-Goldstone modes are long wavelength gapless excitations over the degenerate ground states. And Nambu-Goldstone bosons are derivatively coupled due to a shift symmetry. And effective interactions of Nambu-Goldstones are dependent on both the full symmetry group G in the UV and the unbroken group H in the infrared. Okay. And so the CCWZ procedure has been applied to Chiral perturbation theory to very high orders. And in fact, some heroic efforts went into constructing the effective Lagrangian of chiral perturbation up to order P to the 8th, which is completed only very recently. For example, here, this is a construction of a chiral Lagrangian up to order P to the 6th. This was done in 1999. And the P to the 8th Lagrangian came much later and was completed only in 2018, almost 20 years later. Okay, and moreover, here is a list of the number of independent operators at each order in the derivative expansion. Okay, for a general number of flavor NF, the number go from 2 to 13 to 115 and 1862. And this is, by the way, I need to emphasize, this is including all the external fields included, okay, including the fermions and the photon and so on and so forth. But you see that the number of operators grows exponentially as we expect. Okay. So in spite of the tremendous success of CCWZ in a wide range of topics, there is always something odd about it in my view, okay? And I will summarize it, this something odd about CCWZ as the following question. That is, we know the Nambu-Goldstone bosons are long-range degrees of freedom interpolating different vacuum. So why would its interactions know anything about the broken group G in the ultraviolet? In other words, Nambu-Goldstones should be all about the infrared physics, not the UV. So indeed, Nambu-Goldstone bosons have a very peculiar infrared property that has been known again for more than half a century. But before I talk about this infrared property of Goldstone boson, I want to first talk about something that is not usually emphasized in the textbook, but is very important for my purpose of understanding this peculiar infrared property of Nambu-Goldstone boson. And the only exception is Weinberg's QFT volume 2. Okay, this is the only place where I see this very important point emphasized. Okay, so Recall that the ground state of this Mexican potential is a circle and is characterized by an angle alpha, which is really the polar angle on the xy plane. So now let's bring in quantum mechanics. Quantum mechanics tells us that we can actually form a superposition of all the ground state on the circle. Since these are degenerate ground states, so in principle I can form a superposition, a new ground state, zero twiddle, that is a superposition of all the ground state at the bottom. And for this particular superposition of ground state, you can see that zero twiddle is actually invariant under rotation. Okay, so why couldn't this zero twiddle be the ground state of the system? Okay, that is, if you think a little bit, this is something that it should all occur to us. Why could this zero twiddle be the ground state of the system? And it is rotationally invariant. And this is because there's an important ingredient for spontaneous symmetry breaking to occur, which is the superselection rule, which says that the vacuum expectation value, well, it's not really vacuum expectation. The matrix element of any Hermitian local operator between two different ground states, alpha and alpha prime, vanish. Okay, so that means the ground state of the system is consistent of a disjoint super selecting sector labeled by different alpha. Okay, therefore a stable ground state, when you have this super selection rule, a stable ground state must carry a definite alpha and cannot be a superposition of alpha states. Okay, and this super selection rule actually has an important implication for the S matrix elements involving a soft pion. By the soft pion, I mean that you take a pion and take its momentum to be on shell and goes to zero. Okay, and the way to go about it is the following. Again, recall in quantum mechanics that a momentum eigenstate has the wave function, a plane wave function, e to the I k x. Then a zero momentum eigenstate has a constant wave function. Okay, a constant wave function is not renormalizable for infinite space. And since the pion, interpolates between different vacuum, it turns out that you can show that a zero momentum pion effectively flips the direction of the ground state uniformly in the system. That is, when you have a zero momentum pion acting on an alpha ground state, it effectively take you to a nearby ground state alpha prime. Okay, so this means that any state that has a bunch of hard particles plus a soft pion is equivalent to the hard particles excited over a nearby ground state alpha prime. And therefore, the S matrix element between hard particle plus the soft pions is effectively equivalent to hard particles, matrix elements of hard particle excited over two different vacuum, alpha and alpha prime. And by super selection rule, these must vanish. Okay. So this particular IR property of the Nambu-Goldstone scattering amplitudes was first derived in the context of pions in Lagrange QCT by Steve Adler back in the 1960s. And it is now known as the Adler zero condition. And moreover, it's very important to recognize that it is a universal behavior of Nambu-Goldstone bosons, independent of the symmetry breaking pattern G mod H. Okay, so in fact, in QFT, one can show that the Adler zero condition, okay, that is the matrix element of a bunch of hard particles containing a soft particle vanish, actually follows directly from the shift symmetry acting on the Nambu-Goldstone bosons. And this is hardly surprising, as the shift symmetry is an indication of the existence of other degenerate ground states. And so it turns out that the L0 condition allows for an entirely unsure formulation of Chiral perturbation theory. And it all started from an obscure paper by Susskind and Fry from, again, half a century ago. So this is back in 1960s. Susskind and Fry put up this a paper with the following title: Algebraic Aspects of Pionic Duality Diagrams. Okay, what did they do? Okay, schematically, this is what they did. So they first used the L0 condition to fix the 4-point amplitude of pion. This is the 4-point amplitude of pion, subject to the unsure condition and the total momentum conservation. Okay, and you demand that this vertex, this 4-point amplitude must respect the L0 condition. And after you impose the unsure condition and total momentum conservation, the 4-point amplitude must look like P2.P4 or P1.P3. Okay, and you need to insert some dimension for parameter f with some arbitrary coefficient c. So the L0 condition essentially fixes the 4-point amplitude of pions uniquely after impose unsure condition and total momentum conservation. Okay, and some important comments is that first the Susskind and Fry, they work directly with flavor order amplitudes. And also you can see that there is no constant term in the amplitude because otherwise the L0 condition will not be satisfied. And F here is a dimension for parameter, while C here is an arbitrary number, which in principle could be absorbed into the normalization of F. Okay, so once you have the 4-point amplitude, you know how to build up the 6-point amplitude from the 4-point amplitude by just stitching them together. Okay, so Susskind and Fry did just that. Once they fixed the 4-point amplitude, they built up the 6-point amplitude using the available 4-point amplitude. So this is the contribution they get, and this is the amplitude they get for the 6-point amplitude. Here I'm using the notation that P123 is P1 plus P2 plus P3 squared, and Sij is Pi plus Pj squared. So when you build up your 6-point amplitude using the 4-point amplitude this way, of course, you see that this expression does not satisfy L0 condition. So this is not the correct amplitude for the 6-point pion interaction. So what do you do? Okay, and again, it should be obvious that what you do right now is to introduce an additional contribution, which is the 6-point contact interaction, whose sole purpose is to make sure that the L0 condition is satisfied at the 6-point level. So it turns out that imposing the L0 condition at the 6-point uniquely fixes this particular 6-point contact interaction to be P135 squared. Okay. So Susskind and Fry constructed up to 8-point amplitudes this way, and conjecture that this can be extended to arbitrary multiplicity n. Okay, and I would say this is very striking because the only ingredients they use is first a notion of flavor ordering, which could arise just due to some infrared quantum number given by the unbroken group H. That's the first ingredient. The second ingredient they invoke is the vanishing soft limit in the scattering amplitude. Okay, so in other words, the only construction they use here are the infrared data. They make no reference to the group G in UV at all. Okay, so to me, this is the most striking feature of the construction by Susskind and Fry. That is, they are able to uniquely derive the pion interaction up to 8-point without making any reference to the ultraviolet group G. So naturally, you ask, how general is this approach? Okay, it turned out that the answer is affirmative, but the answer did not arrive until much later when the asymmetric theory strikes back. Okay, So this is when this is where I talk about the rise of modern S-matrix theory. And again, I think it's very fascinating to read through this historic account by Weinberg about the birth of uh, 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 the Chiral Perturbation theory and make a contrast to the resurgence of modern S-matrix theory. For example, Weinberg said that his motivation for working out the Chiral Perturbation theory is that the question naturally arose: is there a way of avoiding the machinery of current algebra by just writing down a field theory that would automatically produce the same results with much greater ease and perhaps physical clarity? And it turns out that, you know, the goal or the mantra of modern S-matrix programmers is exactly the same question with current algebra and the field theory swapped out. In fact, I would say that the modern S-matrix programmers like to ask, is there a way of avoiding the machinery of quantum field theories by just writing down a simple set of algorithms that would automatically produce the same results with much greater ease and perhaps physical clarity? Okay, so this leads us to the on-shell soft bootstrap program that really appeared only within the last few years. So what Saskai and Fry did was the precursor to modern S-matrix program of soft bootstrap. And the soft bootstrap is really the idea that all interaction vertices of Nambu-Goldstones are determined recursively by requiring the L0 condition on tree level amplitudes. Okay, and in particular, the progress is really based on the soft recursion relation proposed by Cliff, Carroll, Jerry, and Tranca back in 2014 and 2015. Okay, and it turned out that there is a parallel algebraic approach seeking to reconstruct the CCWZ Lagrangian using infrared data by recursively imposing the shift symmetry, because after all, L0 condition is equivalent to shift symmetry. But for the rest of this talk, I will mostly focus on the approach of the soft recursion relation. Okay. So, you know, even if you don't work on soft, even if you don't work on the recursion relation, you probably heard that the idea of recursion relation is to take an on-shell amplitude and deform one of the external momenta to the complex plane. Okay, and so for the soft recursion, you know, what we need to perform is an Oleg shift in external momenta. Okay, so we shift every external momenta to the complex plane by deforming it as p goes to 1 minus aiz times pi. Z is a complex variable, and ai is a constant, and we need to require momentum conservation even after the Oleg shift. That means ai times pi must equal 0 so that the total momentum conservation is still preserved. Okay, and now once you perform this Oleg shift, taking z going to 1 over ai, send the momentum to 0. So this is equivalent to taking the self-limit of p. And then, you know, one need to construct an integrand, okay, which consists of the endpoint amplitude with the external momentum deformed divided by the soft factor like this. And the purpose of this soft factor is so that the integrand vanishes like 1 over z raised to n minus 1 power. And therefore, the residue at infinity vanishes. And moreover, there is no pole, even though we are dividing by 1 minus aiz. There's really no pole at z equals 1 over ai because the numerator also vanishes due to the L0 condition. So the only poles are at z equals 0 and when the internal propagators go on shell. Okay, and it's easy to work out that in this case, the internal propagator go on shell at a value of z, and then Cauchy's theorem immediately gives us the endpoint amplitude as a product of two sub amplitudes, where all external legs are on shell, divided by this particular factor. Okay, and so schematically, what we're doing in the self-recursion relation is that we're trying to compute the left-hand side, which contains 3 or 4 different Feynman diagrams, 3 involving a propagator, and the 4th one is a contact term. So this is how what we compute using ordinary Feynman diagram for the 6-point amplitude. But using the soft recursion on the right-hand side, we only have contributions from the factorization channel only. So meaning that there is no contact term involved on the right-hand side. And somehow miraculously, the soft recursion tells us that the sum of these 3 factorization channels on the right-hand side equals the sum of the 4 diagrams on the left-hand side, which includes the contact term. Okay. So a very quick comment on this all-leg shift is that we need to work out what these AIs are in general, but the important point to recognize is the non-trivial solutions for AI don't always exist. And in 4 dimensions, the number of non-trivial solutions is n-5, where n is the number of external momenta. And the general solution for AI is only defined projectively and has a shift symmetry, meaning that the general solution, if you find a special solution for AI, you take an A times the special solution plus a shift. This gives you a general solution, and where the capital A and capital B are arbitrary constants. Okay. So when soft bootstrapping the amplitudes using the soft recursion, it is a non-trivial check that the outcome is independent of these arbitrary constants A and B. And so we will see that this does not automatically happen. And thus we define consistent EFT in soft bootstrap when the amplitude obtained from the soft recursion is independent of the arbitrary constant A and B for all n. Okay. So soft recursion allows one to generalize Susskind and Frey to all orders in the multiplicity n, but the discussion so far has been confined to the leading 2 derivative operators. And in order to really talk about Chiral Perturbation Theory or a general EFT of Nambu-Goldstone, we need to recognize that first, there exist higher derivative operators, which become increasingly important as the energy become higher. And each higher derivative operators come with an uncalculable Wilson coefficient called the Lagrangian constant in Chiral Perturbation Theory. And there also exist topological operators, the Western-Witten terms at higher derivatives. And there are even more complicated flavor structure beyond the single trace operator at higher derivatives. So how does on-shell soft bootstrap incorporate these features? So this is where we introduce the notion of soft blocks. A soft block is a contact interaction carrying n scalars and k derivatives that satisfy the L0 condition when all external legs are on shell. And one can show that for 4 derivatives or less, the soft block exists only for 4-point and 5-point contact terms. And a few comments are the soft blocks are really C's for soft recursion relation, because when you do a recursion relation, you have to start from somewhere. Okay, you need a C to start your recursion. So the soft blocks are C's for soft recursion relation. And they are in one-to-one correspondence with the number of independent operators at a particular order in the derivative expansion. And practically speaking, each soft block represents the lowest order interaction vertex from a particular higher derivative operator. Okay, so just to give you some example, at the order p squared, there are 2 quote-unquote flavor order 4-point soft block. The first one is a single trace 1, 2, 3, 4. These are invariant under the cyclic permutation 1, 2, 3, 4. Therefore, that's why it's called single trace. There's double trace 1, which is invariant under separate cyclic permutation of 1, 2, and 3, 4, and that's why this is called the double trace operator. And at this order in derivative expansion, one can construct 2 EFTs using these 2 soft blocks separately. For example, at the 6-point amplitude, we can construct a single trace 6-point amplitude that is invariant under cyclic permutation 1, 2, 3, 4, 5, 6. And this coincides with the pion amplitudes worked out by Susskind and Bright. Okay, and you can also construct a multi-trace operate at 6-point, and this is, I'm showing you a triple trace amplitudes, and this is not previously known in the amplitudes community. So a natural question to ask is, could there be a mixed EFT involving both the single trace and double trace solved blocks at order p squared? It turns out the answer is no, and I want to show you this example because this is an example where you do not get a consistent amplitude, because when you try to mix the single trace and double trace solved block, at the 6-point, you get an amplitude that depends on this constant B. And therefore, this is not a consistent amplitude. All right. So in the end, we can match the single trace solved block to Nambu-Goldstones in the adjoint of SUN, or SUN cross SUN mod SUN coset. For the double trace, this is matched to the fundamental of SON, which is really the coset is SON plus 1, sorry, SON mod SON minus 1. Okay, and obviously the Chiral Perturbation Theory corresponds to the single trace one. And so there are four 4-point solved blocks at the order p to the 4th, and just quickly show you what they are. And it turns out all 4 solved blocks appear in Chiral perturbation where Nambu-Goldstone transform as the adjoint of the unbroken SUN. Okay, here I'm showing you the direct one-to-one correspondence between the solved blocks and the Lagrangian constant in the order p to the 4th chiral Lagrangian. Okay, and for the fundamental SON, only 2 operators exist, and so these solved block at order p squared and order p to the 4th, they generate all 3 amplitudes from the symmetry breaking pattern SON plus 1 mod SON up to order p to the 4th. And that was for the 4-point solved block. It turns out that there is a unique 5-point solved block at order p to the 4th that involves the epsilon tensor. Okay, so clearly this corresponds to the parity R West-Minor term. Okay, and it's not invariant under the shift symmetry. We know this, that the West-Minor term is a boundary term, so it varies by a total derivative. Okay, and a few comments here is that it turns out that first of all, it's very easy to see because the epsilon tensor here, the West-Minor solved block is non-zero only when the number of flavor is bigger than 5 due to the bow symmetry. Okay, and when introducing West-Minor solved block to the SUN adjoint EFT, all amplitudes are consistent. Whereas if we try to introduce the West-Minor, the Witten solved block to the SON EFT, we can't get a consistent 7-point amplitude by doing the solved bootstrap. Therefore, the resulting EFT is inconsistent. Okay. However, there's a subtlety here in the SON EFT for the particular case of 5 flavor, because in this case, 3 of the 7 external particles must have identical flavors, because we have NF equals 5 and we have 7 external particles. So 3 of the 7 external particles must have identical flavors. So therefore, we need to symmetrize a 7-point amplitude with respect to these 3 particles due to bow symmetry. And miraculously, after symmetrization, a consistent 7-point amplitude now emerges for NF equals 5. So in the end, for the adjoint SUN, the West-Minor Witten term exists for NF bigger than 3. And since NF is n squared minus 1, and here is the NC, so that means we can have a West-Minor term for all SUN with n bigger or equal than 3. Whereas for the fundamental of SON case, the West-Minor term is absent except for NF equals 5. And this is the case that so we conclude that the Western middle term exists only for the S405 fundamental representation of the Nambu-Goldstone boson. So it turns out that these results agree completely with those from group theoretic consideration based on the fifth theorem cohomology group. So to me, this is a big mystery that how do L0 plus both symmetry know about the cohomology group of the G mod H coset? Because as you see, the only ingredients we use here are the L0 and both symmetry. But somehow miraculously, we can reproduce the result using the fancy theorem cohomology for the Western middle term. Okay. So let me pause a little bit and reflect on what we have learned. I hope I've convinced you that interaction Nambu-Goldstone can be deduced entirely from infrared data from L0 plus the infrared quantum numbers without reference to the broken group G. And an important corollary is that the self-interaction Nambu-Goldstones with identical infrared quantum numbers must be universal, independent of the G mod H coset. And this universality has important implications for composite Higgs models where Higgs boson arises as a pseudo Nambu-Goldstone, but I don't have time to go into that today. But I do want to explicitly check for you this universality of Goldstone interactions. So going back to this early example of a complex Nambu-Goldstone charge under the U1 group of H, okay, we have two complex Goldstones and they have identical infrared quantum numbers because they are both charged under U1 group. And therefore, the universality would dictate that the self-interaction of in these two cases should be the same. And lo and behold, in these two, for the first interaction, if you make a replacement of F going to 4F, you will see that these two interactions, these two Lagrangian are completely identical to each other. Okay. So now let's apply the unsure method to the counting of operators in Chiral Perturbation theory. As is well known, the construction of independent operators in EFT is notoriously difficult due to the complicated operator relations such as integration by parts, equation of motion, and etc. and etc. Okay, so for example, in Chiral perturbation, the leading order equation motion looks like this, where the covariant derivative of something is defined as in the usual way using this associated gauge field. And making things worse for Chiral perturbation, there are additional relations imposed by the symmetry of the coset in Chiral perturbation, which is given by these two relations, okay? And it turns out that these complicated operator relations manifest themselves trivially in soft block. For example, integration by parts is equivalent to total momentum conservation in the unsure approach. Equation of motion is equivalent to the unsure condition for external momenta. And the symmetry relations are automatically incorporated in soft bootstrap. So in the end, soft blocks are an efficient way to count the number of independent operators at each order in the derivative expansion. Moreover, all three amplitudes can be generated recursively once the soft blocks are obtained. Okay, so together with Lin, Tom, and Abhishek, we enumerated all soft blocks in Chiral perturbation up to order P to the 10th. Okay, for the purely mesonic case, so these correspond to turning off the spin 1/2 and spin 1 external fields in Chiral perturbation. And also for simplicity, we work in general spacetime dimension D and general flavor and F. Okay, so here is number of soft block in going from P to the 4, 6, 8, 10. Okay, so we check that since the existing literature only has Lagrangian up to P to the 8th, so our number agree with the existing literature up to order P to the 8th. And moreover, we make a prediction at order P to the 10th, that is the number of purely mesonic operator is 1451. And so it turned out there are other mysteries waiting to be explored for Chiral perturbation. So I'll give you two quick examples. One example is the subleading single solve theorem. Again, the calculation of single solve theorem has a long history, dates back to the early days of QED. And in both QED and gravity, it is well known that S-matrix elements factorize universally when you take the single solve limit. That is, you take an n+1 point amplitude and you send one of the external momentum to 0, then you find the amplitude factorized universally in terms of some solve factor times the endpoint amplitude in QED and gravity. Okay. And for Nambu-Goldstones, you can do the same thing. Let's compute the single solve theorem. You take the n+1 point amplitude in Chiral Lagrangian, and you send one of the external momenta to 0. Then the other L0 condition tells you that the left-hand side, the right-hand side, the solve factor start from the leading order is start from first order in tau, because as tau goes to 0, D has to go to 0. Okay. So the question here is, what is this coefficient sitting in front of the tau? Okay, for QED and gravity, the coefficient here is the endpoint amplitude. But the problem for the Nambu-Goldstone or for chiral perturbation theory is that only even point amplitudes exist due to parity. Okay, so you only have the 4.6 point, 8 point amplitudes in chiral perturbation. So when you take the single soft limit of an even point amplitude, you would have gotten an odd point amplitude, but there is no such thing in chiral perturbation. So this is the question that people could have asked back in the 1960s. What is the coefficient of this tau when you take the single soft limit for Nambu-Goldstone? Okay. It turns out that the subleading single soft limit in chiral perturbation wasn't computed until a few years ago. First using this Cacciazzo-Hay-Yuan from a CHY formulation of scattering amplitude. And by using that, Cacciazzo and collaborators found that the coefficient Mn, as I explained to it, does not exist in chiral perturbation theory. However, the Mn can be given as it can be interpreted as the scattering amplitudes of an extended theory containing cubic bi-adjoint scalars interacting with the pions. Okay, and with Zoe, we derive the same result in QFT using word identity. So the natural question is, what are the phonological implications of this particular observation? Can we even observe this extended theory experimentally? Okay. And the second example is there is actually a very neat double copy structure buried inside the chiral perturbation theory at the order p to the fourth. At the leading order p to p squared, there is a trivial double copy one can write down for chiral perturbation. That is, the two derivative nonlinear sigma model can be written as two derivative non-sigma model double copy with a bi-adjoint scalar whose Lagrangian that I show here. Okay, and this is trivial relation because this quote unquote this double copy kernel, this chaotic kernel, is really 1 over the phi cube itself. So that's why in this sense this is a trivial double copy. But when you go to the order p to the fourth, among the 4 order p to the fourth operator, one of them has a non-trivial double copy structure. That is, the 4 derivative operator can be written as a double copy of the 2 derivative operator with a Yang-Mills theory interacting with bi-adjoint scalar whose Lagrangian look like this. Okay, so again, what's the implication for chiral perturbation theory? Can we use this double copy, for example, to simplify the calculation of amplitudes for a particular order p to the fourth operator in chiral perturbation theory this way? Okay, so this is pretty much all I want to say today. So some concluding remarks is that first, I hope I convinced you that interaction of Nambu-Goldstones can be determined almost entirely from the infrared using the L0 condition as the defining property. Okay, and the nonlinearity in the Nambu-Goldstone interactions arises entirely from the infrared physics. What's being broken in the UV is irrelevant for the most part. And the complete effective Lagrangian for chiral perturbation can be formulated in an entirely unsure perspective when external sources and fermions are neglected. And here is an interesting question is because so far I'm focusing entirely on the mesonic sector of the chiral perturbation theory. So we know that there are the nucleons and there's photon in the chiral perturbation. So what happens when we put back the photon and the nucleon in chiral perturbation theory? In other words, is there still a soft bootstrap when we turn on the photon and the nucleon? So I'll stop here right now and see if there is any question.